This is just a little video I wanted to do with some of the test equipment that I have laying around. I've got all sorts of different stuff. I've got probably 5 or 6 oscilloscopes at this point in various states of disrepair. I think I only have 2 that actually work worth a damn. But one of the things that I've been wanting for a while is a decent frequency counter. I had a digital one that decided to just up and stop working, and at the time I didn't know enough about them to really get into it and try to repair it. I'll probably wind up doing that later, but I really wanted one with a Nixie tube display. You think of like the older Hewlett-Packard models. I actually have a whole bunch of cards for those that are a combination 4-bit BCD counter with a different count style. It's really goofy, like 1462 or something. I don't know. It's really oddly weighted. Either way, I wanted one of those, but HP original equipment is very well built, and it also commands a pretty decent price on the used market, unless it's totally junk, in which case it's just, parts value. So whenever I go to radio swap meets or ham meets, I always like to look out for neat old test equipment that use the type of display that might also be kind of useful. And a while ago I picked up a frequency counter for RF stuff that does work moderately and needs to be fiddled with, but this one, this Atec right here, I got from a meet up in Shoreline, the Puget Sound Antique Radio Association, and I think I got it for like $5 or something, and I could tell it had a Nixie display. I can't remember how many digits this is. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, this is an 8-digit display, and then the 9th is a indicator for like seconds, hertz, or whatever. But I loved it because it had these great big aluminum rack mount handles and everything. The brushed aluminum face. It looks really neat. But what was really cool about it, as you can see from the top here, this entire thing is put together with edge cards. So there are no integrated circuits in this entire thing. The entire unit is built using RTL logic, or that's kind of redundant. It's a resistor transistor logic. And when I first got it and tried to power it up, I got nothing. I think 1 or 2 of the digits lit up. The cooling fan on the back kicked on. Nothing blew up, mind you, but it didn't respond the way I was kind of hoping it to. And the other problem is, when I tried starting to service it, there is no information out there on these. I could find a few random Atecs for sale on eBay, but no manuals, no schematics, no product information, no build dates, nothing. So I'm kind of on my own when it comes to servicing this beast. So what I started to do was effectively try to identify what each of the cards in this machine actually do, because each one has a separate function. And one of the first things I did was try to identify the power supply segments. Obviously, you've got some multi-section electrolytics back here. We've got the crystal oscillator unit that's actually got an octal socket base, but unfortunately they didn't fill in any of the information, like what frequency it runs at, what voltage it uses, and all that kind of junk. I'd kind of like to know what the base clock of this unit is, but they didn't write it down. But I started at the power supply, and that's all the way over here at this card. I can try to wiggle these out. Some of the edge connectors are pretty tight. And I've already done some work to this, so you can see I replaced some of the electrolytics here. We've got some diodes set up for rectification, and we've got these 2 potentiometers right here, and I looked at that, and someone had penciled in plus and minus over on the side, and I only just recently determined that that's actually for the positive and negative supply voltages. The positive one actually adjusts a positive 10 volt supply output that I located, but I still haven't figured out which supply the negative one adjusts. I've probed all over the insides of this thing and come up with nothing. But I did notice a whole bunch of these really nice big black heat marks here and underneath where these resistors are. Not the best insulation. The original PCB traces were pretty badly damaged. In fact, 2 of the resistors that were on there had just blown up completely. So I reflowed solder on here. I replaced 1 or 2 transistors, replaced the electrolytics, and then I found the closest resistor values I could swap into here. And I figured, okay, you know, power supply done. That should make it fire right up, right? No. I cleaned all the contacts and all the cards, tried to figure it out, nothing. So the next step is, well, then what the heck did all the other cards do? Well, I just recently built an all-transistor Nixie clock. I'm going to have to get some video of that on the channel here soon. So the way I built that was I had a board that was nothing but the counters using transistor-based flip-flops. Now, a normal flip-flop only requires 2 transistors and a few other assorted components to make, and if you chain them together in a ripple counter style, you can get a BCD output if you set up a reset correctly. And while I was looking at all these cards, I took note of the fact that most of these in this section here are duplicates of each other. So if we take a look at, try and find, here we are. So I was looking at these and they are very snug in there. And I thought, well, each of these digits, if this is all transistor logic, has to have a counter, and it also has to have a low voltage to high voltage decoder. Okay, we're going to have to get... Unfortunately, the only way to get these out anymore is to use a little bit of force. So I try to be... There we go. Try to be careful not to damage the traces. Anyway, so I looked through there, and I noticed there seemed to be one of these cards for each digit, and the board just ahead of it, which I'll show you in a minute, there's also apparently one of those for each digit, except for the one that indicates the function, because that can just be operated with a switch connected to ground, no big deal there. But I'm looking at these and going, you know, these are all very symmetrical. The component layout is exactly the same on every card, and then looking at how many transistors there are, let's see what we got. Well, 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, barring the lower half of the card, 8 transistors, that's roughly what you'd need to get a full 0 to 15 count in binary. Each pair of these transistors can be a flip-flop, either however you want it to be. And on the underside of the unit, looking at the connections between this card and the one ahead of it, I noticed that there were exactly 8 connections between each of the pairs. And 8 connections is how many you need for a full binary decode if you want to go from 0 to 15 or even 0 to 10 for that matter, or 0 to 9 for that matter. Because you need your 4 standard ones, A, B, C, and D, or 1, 2, 4, and 8, and then you also need their complements. With medium scale stuff like 7400 series logic, if you have a 7490 decade counter and you couple it to a decoder like a 7447 for an LED, a 7-segment LED display, you only connect 4 lines to get a 0 to 9 output. And the reason for that is because the decoder chip already has a built-in inverter to get the complements of the A, B, and C output to get A naught, B naught, C naught, and D naught. Well, with these, those outputs are already being passed to the next card, so if this is the counter, the next card has to be the decoder. Now, as for the rest of the transistors on here, I thought, well, that's a lot of them for a counter, and I only just realized on the back of the unit there's a switch that says storage. This unit's display will constantly update with the sample rate. So every time it blinks, it'll take an input, it'll count it, and then it'll display it at the same time. But if you use the storage option, the counter module will run in the background and count the information, but then these second transistors here are acting basically as a latch. They'll take the information counted, and when the gate pulse comes in, it'll shove that information to the decoder, and it'll be updated. So I'm guessing with storage off, these just pass clean through, so whatever data is already on the counter just goes straight through the buffer or through the latch and straight to the decoder, whereas with the storage active, it'll hold it, and then when the next gate pulse comes in, it'll push it out, or basically it'll become active and push it to the decoder. That sort of thing. So obviously we've got counter cards here. And then the next guy up here, which I've taken these out so many times you'd think they wouldn't be so stubborn, but that's just how it works. Here we have, these were the easiest ones to define because there's literally not much going on here, and I thought, well, You had a bunch of resistors, they're all pretty similar values, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, oh, exactly 10 transistors on there, and everything's very nice and clean. Well, this is our decoder board, and you 0 through 9 decoded output. Very simple. And so my first thought was, well, I look through and I see if there's any obvious damage to the cards. A few of them had 1 or 2 transistors replaced with similar values or similar components. I thought, well, maybe those are bad. Maybe there's something wrong with them. Cleaned all the pins. I tried making some substitutions with modern components. However, not all of that has worked out. However, during the testing phase with the unit, I actually blew the fuse on the high voltage section because I figured, well, it's possible that all the decoder cards are actually working like they're supposed to, but if we have no gate pulse to actually trigger a signal input to the counting cards, then nothing's going to happen. And it's possible that all the decoder cards are actually receiving an invalid input. If it goes above and beyond 9, these counters are obviously capable of doing that. If they don't reset, if there's something wrong with the logic and they go above 9 and they start going 10, 11, 12, 13, 14, 15, these are not going to show anything. And more often than not, you'll just get like a blur of several of the cathodes illuminated at the same time, which some of them were doing that. So I figured, all right, well, skip the cards for now. We need to take a look and figure out why the gate pulse is not running. So the first thing I did was trace back to the oscillator, which is our time base. I checked to make sure that that was actually doing something, and I got a nice sinusoidal output from that. So obviously we're getting a signal from there, and then I tried doing my best to trace it through and figure out where the hell it was going, and got nowhere. Because the wiring in this is tiny and bundled, and extremely hard to track down with a schematic. So I thought, okay, well, can't figure that out. So let's take a look at where the lamp itself is connected, because obviously the lamp is neon, so it's got to have a high voltage driver. That high voltage driver has to be driven by the gate pulse, so maybe I can backtrack it from there. Well, I get over to that portion and find that card, which is this next one just ahead of the power supply, and I can't find anything really wrong with it. It looks okay, more or less, but I was measuring some of the voltages at the bottom, and I realized, well, all of these main decoder cards, obviously, are going to have at least 2 things in common. They need a ground, obviously, which they all have. There's a common wire running through for ground, but they also need to have a supply voltage. I'm used to seeing 5-volt supplies for TTL and CMOS stuff from the 70s, but with transistor logic like this, you'll also see things like negative 25 volts. I know that HP used a whole slew of varying voltages to run their cards with. And I figured, alright, well, there are 2 common connections with all these cards. One of them has to be the supply voltage. And when I measured that rail, I was getting something in the neighborhood of maybe a half a volt, like negative 0.4. It was pretty pathetic. And I thought, well, these cards obviously can't run on that. Maybe it's just a bias voltage. But it didn't seem to make any sense that they would run that low, and every so often there's a decoupling capacitor to pick up transient spikes, and they're rated at least 25 volts. So I figured, alright, well, it's got to be below 25. It's got to be high enough to drive these, maybe 15 or 16 volts. So just on a whim, I disconnected the power supply's rail from the rest of these. I left the high voltage section intact, but I disconnected the low voltage, what I assume was a low voltage rail, and I jacked in my Eclec Precision power supply and turned it up to about 10-15 volts, and what do you know, suddenly the gate pulse lamp starts to illuminate. The reset button causes all of the digits to illuminate with a 0, or close to the you can get, and it actually seems to do something. However, I drew an enormous amount of current on the supply, so obviously there was something kind of funky with it. So I figured, alright, well, obviously that voltage is wrong. There's got to be something wrong with the power supply. But after I disconnected my Eclec, I suddenly realized that the unit was completely stuck in the reset position. Pushing the button did nothing, and I was getting nowhere quickly because obviously I had damage to the unit in some fashion. But even more ironically, when I fired it up again and tested the power supply's output, I was actually getting negative 15 volts on the rail that I was originally getting negative 0.4. So whatever I did with the power supply kicked this thing in the butt and actually got the PSU functioning more or less correctly. So I hooked that back up. Still got the reset problem, so obviously I fried something in that. So I went back, traced through from the reset button, which had the same voltage at either side of the pins, so kept going from there, found the next card where it seemed to connect to, and found a pair of diodes directly connected to it that were both toast. And I tell you what, I replaced both of those with generic 1N4148s, and as soon as I put that card back in and fired it up, I got a display. And even better than that, not only did I get a display, but I got a gate pulse. And that was what is truly important. So every time that gate lamp illuminates, it's basically triggering the signal to go through the cards and all that junk. Anyone who's familiar with the frequency counter, or at least how it works inside, should more or less have that idea. Now I'm going to go ahead and shut my overhead lamp off here because it does bad with the Nixie display. And right now I've got it on a test cycle. So we can see that it's really just looking at whatever frequency it's set on. I still haven't quite figured out what it is. I think it's around 55 kilohertz, something in that neighborhood. But now what we're going to go ahead and do is we're going to switch it up with the frequency setting, and we're going to put it on the frequency divided by time base. And we set our time base multiplier for 10 milliseconds, and we can see that that's, yeah, I think it's trying to aim for about 50. But yeah, I love these things because they're just fun to play with. Now I mentioned earlier about the whole storage thing, so let me show you what actually that happens. So we got our sample rate turned up slightly more, medium high, but if we notice, we can see the rapid counting because the counters are directly passing through. But if we engage the storage option back here, every gate pulse, now we just see everything change nice and clean. And if we switch back to the whole frequency divided thing, you notice we don't have that rapid buildup. We just have a very stable change. I can crank this sample rate up pretty good, actually. We can kind of see it twitch there. But the whole point of that is to make the output look a little more stable. And if we just go ahead and switch it off, we can let it run its course. Or if we do something cool like period, that's always neat. And we can see that when we start doing things with the time base and we modify the multiplier switch here, we can actually change the last two with, say milliseconds, seconds, etc. And there's also a remote setting. This thing has a pair of SCSI style plugs in the back, so this thing could be remotely driven from another piece of equipment, and it looks like it has the ability to pass the BCD outputs from these cards to another display, I suppose. But no, this thing is just really, really cool. Now let's re-engage the storage option here. But yeah, you can do, this thing is set to do a whole bunch of stuff. Most of what I want to get out of it is effectively just checking for frequency and making sure that some of my equipment is calibrated, especially my signal generators. I need to make sure that when I'm trying to align a radio, I am actually setting the thing at 455 kilocycles. So I mentioned earlier that I had done some work. Now, I don't know if I caught that on camera, but there were some of the digits that didn't turn off immediately. The reason for that is because I've been shuffling around the decoder cards in this machine to get the ones that all work perfectly towards the end of the row here, and the ones that are at the very end, well, they've got some issues. So let's try and grab one here. So some of these have got problems, and I've tested them to make darn sure that there's not something totally blown out. I swapped them through to see if they would work at another digit, and if they don't, they don't. On some of these cards, though, I replaced one transistor with a modern one. These are all PNP 70-volt collector emitter voltage rated, and I didn't have anything that directly matched that, so I just figured, oh, if I stick a PNP high voltage transistor in there, maybe the biasing will be more or less correct, so it'll run that way. Well, as it turns out, if you have 9 transistors specifically biased at one point and you introduce a transistor with not exactly the same ratings, that one transistor is going to get favored pretty heavily. So much so to the point that when I turn this thing on, so we just pulled the card that had the 7 by default on, and I can actually show you that by dropping that back in here. And let's reset this to 0 here. This card also, by the way, it really, really likes to reset to either 8 or 4, but if you play with the control there, we can eventually get it. Yeah, there's something goofy going on with that circuit. But anyway, if we drop this decoder back in here and we plug it in, you'll notice the first thing that comes up is 7, and if we try hitting reset, it doesn't want to do it. Now I've tried swapping out counter cards as well, and there's no difference in the operation of the counters. The decoder cards themselves have an issue. So it's entirely possible that one of these things, the transistor, has effectively just become a very low resistance short. And it's preferable, it's preferring one cathode to all the other ones. And I've actually done that with the next 2 digits simply by introducing a non-original component that has slightly different characteristics. It turns that one on, and to the point where when it does actually conduct another numeral, you can't really see the result. So to get the best possible functionality out of this machine, I'm going to attempt to replace all the transistors on one decoder card with MPSA 92s just to give it a shot and see if it works. And if that doesn't pan out, I do have the NTE replacement number for the original component, and I can just do it that way. But just wanted to do a little show and tell on this guy, because I love equipment with Nixie tube displays, and a lot of the people that use this stuff love it for that exact same reason. Because seriously, when you start looking at 7-segment displays all day, having a true form digit like that and being able to see it change the way you can with the storage off on this, I mean, that's that right there is science fiction prop gold. Yeah, I can't tell you how many times I've spotted Nixie tube equipment in the background of 50s and 60s and even later sci-fi stuff. Hell, I think even the Death Star had some Nixie tube displays built into it. But yeah, that's that for now. I'm basically just going to look at doing some final touch-up work on some of these cards, and then hopefully I can get a good signal generator to calibrate this on to make sure that what it's measuring is actually accurate. But I don't have an operator's manual, so I don't know if I'm setting the input levels and all that exactly the way they should be. Just kind of winging it at this point. But yeah, that's the Atec Nixie frequency counter. I was actually able to get all of the work done to make this thing function in a few hours last night by pure happenstance. So super happy. I think I've had this thing for over a year and haven't gotten it to work yet. So.